Welcome to the deep dive, ready to untangle reality itself.
Sounds intense.
Well, at least the Newtonian version of it.
Yeah.
Forces, motion, friction, all those physics concepts. We'll see how they make our world work the way it does.
It's amazing how physics, which people think is this super abstract thing, is actually the key to understanding so much of what we see and do every day.
Exactly. Today we'll see how forces and motion and even friction are woven into everything around us.
It's true.
Okay, so to start, I guess the foundation of it all is force, right? We kind of have a feel for what force is, I think, but how's it actually defined in physics?
Yeah, you're right. We all kind of get what force is, intuitively. But in physics, it's any interaction that, if nothing's working against it, it'll change how an object moves.
So basically, it's a push or a pull.
Exactly. A push or a pull that can make things move or stop moving or, change direction.
So, okay, when I'm trying to, open a really stubborn jar, that's me applying force.
Yes.
And then when it finally opens, it's because the force I was using was stronger than whatever was keeping it stuck.
Exactly. And what's even wilder is that everything we experience, from a gentle breeze to the weight of a book you're holding, it all comes down to these fundamental forces of the universe.
Whoa, fundamental forces. Sounds kind of cosmic.
It is cosmic.
Yeah.
There are actually just 4 fundamental forces: gravity, electromagnetism, and then the strong and weak nuclear forces.
Okay.
Those last 2, the nuclear forces, we don't really see them in action on an everyday level. They're more about what's happening, inside atoms. But gravity and electromagnetism, they shape pretty much everything we experience.
Yeah, gravity is what keeps me from floating off into space.
Right.
And electromagnetism is behind, well, I guess anything electrical.
Yeah. But here's the thing. How do those forces actually work? Because they don't need to touch anything to, have an effect.
It does seem kind of magical. With a magnet, it can pull stuff towards it without even touching it.
Exactly. It's like an invisible force field, right?
Yeah.
That's what's cool about these forces. They can act at a distance. Think of it like they create these fields of influence, like with gravity.
Okay, so that's forces acting at a distance. But then you have forces that need to, directly touch something. Like when I'm pushing a shopping cart.
You got it. Those are called contact forces.
Okay.
And even with that shopping cart example, it's more complex than you might think.
Oh, how so?
Well, you're pushing the cart, right? But the cart's also pushing back on you. And get this, with the same amount of force.
Whoa.
That's Newton's third law. Every action has an equal and opposite reaction.
Okay, so every interaction is kind of like this perfectly balanced exchange of force.
Exactly.
And there's that other force, that contact force, I can't remember what it's called. The one that acts perpendicular to a surface.
Oh, you mean the normal force?
Yes, the normal force.
That one's all about making sure objects don't just pass through each other.
Okay.
Picture this. You've got a book just resting on a table. Gravity's pulling the book down, obviously. But the table's pushing back up on the book with an equal force. That's the normal force.
It's like this constant invisible support system.
It is.
Okay, so we've got forces acting from a distance, forces from contact. Are there other types of forces too?
Well, there are forces that come from things being attached to each other. Think about tension.
Tension.
Yeah, if you're playing tug of war with a rope,
Yeah.
you're feeling the tension in that rope. It's a force that gets transmitted through the rope when it's pulled tight.
Oh, right. It's how we can pull things or hang pictures on the wall.
Exactly.
Okay, so we've got forces. They're like these pushes and pulls that either act over a distance or through direct contact. And they're behind everything that happens in the world, right?
Right.
But how do we actually go from understanding forces to understanding how things move? How does it all fit together?
That's where Newton's laws of motion come in. They're like the rule book for how objects behave when forces are acting on them.
Okay, Newton's laws. Those are pretty famous.
They are.
Let's start with that first one, the law of inertia.
Okay, so Newton's first law says that an object that's at rest is going to stay at rest, and an object that's moving is going to keep moving at the same speed and in the same direction unless there's a force that acts on it.
Objects just want to keep doing what they're doing.
Yeah, and that's inertia, that tendency to resist any change in motion. It's why you wear a seatbelt.
Oh, right.
If the car suddenly stops, your body wants to keep moving forward at the same speed. The seatbelt's there to provide that force to stop you safely.
Okay, so it's objects have this, stubbornness, unless a force comes along and makes them change.
Exactly. But what happens when a force does act on an object? That's where the second law comes in.
Newton's second law. That's the one with the equation, F ma. I remember that from school.
You got it.
What does that really tell us about motion, though?
It tells us that how much an object speeds up, its acceleration, it depends on the force acting on it and how much mass it has.
Okay, so a bigger force, bigger acceleration,
Right.
but a heavier object
Mm.
needs more force to get it going.
Precisely. It's why you can, push a bicycle pretty easily to get it moving,
Uh-huh.
but you'd need way more force to get a car moving.
Makes sense. Okay, and now for the big one, Newton's third law.
The famous, for every action, there's an equal and opposite reaction law.
Right, that's the one about the shopping cart pushing back on you.
Exactly. It's important to remember that those forces are acting on different objects. You're pushing on the cart, and the cart's pushing back on you. The Earth pulls on you because of gravity, and you pull back on the Earth with the same force.
Whoa. Okay, so it's like this cosmic dance of balanced forces everywhere we look.
I like that. A cosmic dance of forces.
No.
But how do we keep track of all these forces and what they're actually doing to an object? This seems complicated.
Right.
Well, that's where free body diagrams come in.
Free body diagram.
Yeah, it's a tool that physicists use to visualize all the forces acting on an object. We basically represent them as arrows on a diagram.
Oh, okay, so it's like a force blueprint.
Exactly. We can strip away all the other details and just focus on the forces.
I'm starting to feel like a physics detective.
I love that. But before we go solve any mysteries, there's another force we need to talk about. One that's always there, sometimes helpful, sometimes a pain.
What's that?
Friction.
Friction. It's the force that's like always trying to slow us down, right?
Yeah, it's the force that opposes motion between two surfaces that are touching.
Right.
It's the reason stuff eventually stops moving unless there's a force to keep it going.
Gotcha.
But here's the thing. Friction can actually be really important.
Oh, in what way?
Friction. It's more important than people realize. Like, imagine trying to walk on a surface with, zero friction.
Okay, yeah, that sounds pretty tricky.
Like trying to walk on ice skates, but even slipperier.
I could see the problem.
You wouldn't be able to push off the ground at all. You'd just be, waving your arms around.
So friction is what gives us that grip we need.
Exactly. And it's not just walking, driving a car. That relies on friction, too.
Oh, right, yeah.
The friction between the tires and the road, that's what lets you speed up, slow down, even turn the steering wheel. Without it, cars would be spinning out of control all the time.
So friction is kind of like the unsung hero, keeping us grounded and in control.
I like that, the unsung hero. But then why are we always trying to reduce friction in machines and stuff if it's so important?
Right, that's what I was thinking.
Well, it's because friction can also be a problem. In machines, it can cause parts to wear out faster, create heat we don't want, and make things less efficient. So engineers are always looking for ways to reduce friction where they can.
So it's about finding the right balance.
Exactly. Enough friction for things like walking and driving, but as little as possible where it's just causing problems. And there are all sorts of ways to do that. We use things like oil to reduce friction.
Oh, right, lubricants.
Yeah. And we polish surfaces to make them smoother. Or we streamline the shapes of objects so they move through the air with less resistance.
So we're basically manipulating friction depending on what we need.
Yeah, we can boost it, reduce it. It's pretty cool. And understanding how it all works, that's how we can do things like design super fast race cars and things like prosthetic limbs that move more naturally.
It's amazing. Okay, so before we were talking about free body diagrams, can you remind me how they work again?
They're really helpful. They help us really see all the forces that are acting on a specific object.
Right, okay.
So imagine you're, I don't know, pushing a box across the floor.
Uh-huh.
And it's, one of those rough floors, so there's a lot of friction.
Yeah, I can picture that.
We can draw a free body diagram of that box. We can show gravity pulling it down, the floor pushing up, the friction working against you, and then your force pushing the box.
Okay, it's like all these forces are in a tug of war. How do we actually figure out what the box is going to do? Like, will it move or not?
That's where Newton's second law comes in handy.
Oh, right.
Yep. We can use that equation to see how the forces relate to the box's acceleration. Basically, if your push is stronger than the friction, the box will move.
Okay, so the harder I push, the faster it'll go.
Well, up to a point. Now, what if that floor suddenly got smoother? Like way smoother?
Less friction.
Oh, right.
So I wouldn't need to push as hard
Exactly. That's why we put oil in engines and things like that.
to make things move more easily.
And wheels. Don't forget wheels.
Oh, right. Wheels are amazing. They make it so much easier to move things around.
Exactly. They reduce friction a ton,
Yeah.
so we can move things much more efficiently.
Okay, so changing gears a little bit.
Yeah.
We talked about pulleys before.
Yeah.
What are those all about?
Pulleys are a great example of how we can, use our understanding of forces to do really cool things.
Okay.
They're basically simple machines that let us change the direction of a force.
Okay.
And we can even use them to reduce how much force we need to lift something heavy.
So it's like we're kind of tricking gravity.
That's a good way to put it. Like, think about trying to lift a really heavy weight straight up. It would be super hard, right?
Yeah.
But if you use a pulley, you can pull down on a rope instead. The pulley redirects that force upwards to lift the weight.
Okay, so it's like changing the angle to make it easier.
Exactly. And there are all different kinds of pulley systems with different levels of what's called mechanical advantage. A simple pulley just changes the direction of the force, but a system of multiple pulleys can actually reduce how much force you need to lift the weight.
That's amazing. It's like bending the rules of physics.
Mm-hmm.
But how do you even, analyze a pulley system? How do you know how much force you need?
Well, we use the same principles we've been talking about. Free body diagrams
Okay.
and Newton's laws.
Right.
You draw free body diagrams for each of the objects in the system.
Okay.
The weight, the pulleys, the ropes, everything. And then you can apply Newton's second law to each one to figure out the forces and how they all work together.
It's like solving a bunch of interconnected force puzzles.
It is. And it's pretty amazing what we can do with these ideas. Physics is really about understanding how the world works at a deeper level.
It kind of feels like a superpower,
Mhm.
being able to see these forces and predict how things are going to behave.
It is a kind of superpower.
Okay, so we've covered forces, Newton's laws, pulleys. I feel like my brain is getting a workout,
It's good exercise.
but there's still more to explore, right? Like friction.
Yes. Friction is more complex than it seems at first glance.
Okay, so friction. Back to that. I'm ready to learn more.
It's definitely worth another look. Like we said, people often see friction as a bad thing, right? Something that slows things down.
Right, yeah.
But without it, things would be so wild.
Oh, why is that?
Think about what it'd be like to try and walk on, a completely frictionless surface.
Mm-hmm.
You'd be like trying to walk on ice skates on an ice rink, but way worse, even slipperier.
Oh, I get it. You wouldn't be able to get any grip.
Exactly. You wouldn't be able to push off the ground. You'd just be flopping around.
So friction is what lets us walk.
It is. It gives us traction. And it's not just for walking. Driving a car, that depends on friction too.
Oh, yeah, right.
It's the friction between your tires and the road that lets you start moving, stop, and even steer. If there was no friction,
Yeah.
cars would be totally out of control, just spinning out everywhere.
So friction is kind of the unsung hero in a way. It keeps us from slipping and sliding all over the
It
place.
keeps us grounded. But then why do we try to reduce friction in machines and stuff? Isn't it important there too?
That is what I was wondering.
Well, because in those situations, friction can cause problems.
Oh, okay.
Like in a machine, friction can make parts wear out. It creates extra heat.
Yeah.
And it makes the whole thing less efficient. So engineers, they spend a lot of time figuring out ways to reduce friction in machines.
It's all about finding that balance then.
Exactly.
Yeah.
We need some friction for things like walking and driving, but too much. That's where it starts causing problems.
Okay, I get it.
And the ways we manage friction are so cool. Think about oil.
Uh-huh.
It's a lubricant. It basically creates a really slippery layer between surfaces so they don't rub against each other so much.
Okay.
We also polish things to make them smoother,
Oh, right.
to get rid of any bumps and ridges.
I see.
And sometimes we design things to be really streamlined so they cut through the air more easily. Think about race cars.
So we're manipulating friction depending on what we're trying to do.
We are. Sometimes we want to make things more slippery. Sometimes we want more grip. It's all about using what we know about friction to solve problems and design things better.
So it's kind of like a strategic thing.
Yeah, we're playing a strategic game with physics.
Yeah.
And knowing how it works lets us do some incredible stuff, from designing those high-performance race cars we were talking about to making artificial limbs that move more like real ones.
That is pretty cool. So we've covered forces, we've talked about Newton's laws, we've even outsmarted gravity with pulleys, and now we've explored the mysteries of friction. I'm feeling a lot more enlightened.
Mission accomplished.
It's really amazing how all these things, forces and motion and friction, they're all around us, shaping how the world works in ways we don't even realize.
It's true. Physics isn't just about equations and formulas and stuff. It's a way of looking at the world, seeing the forces at play and everything.
And that's what makes it so fascinating.
Oh,
Well, to everyone listening, thanks for joining us on this deep dive. We hope it sparked your curiosity about the world around you. Until next time.